Irv Mendelssohn is Dr. Irv Mendelssohn is a professor with Louisiana State University, and he's going to be talking with us about impact and recovery of wetland vegetation. And a fun fact about Irv is that I like to get fun facts about my guest speakers. And his fun fact is that my favorite hobbies have been skiing and wine tasting, not always at the same time. All right, take it away, Dr. Mendelssohn.
Very good. Well, hello, everyone, and thanks, Emily, and good afternoon to everyone. So my objective today is to provide an overview. See if this will work. An overview of Deepwater Horizon impacts and coastal wetland vegetation, and to discuss factors controlling impact and recovery. So this presentation is based on a GOMRI-sponsored effort led by Brian Roberts at LUMCON to synthesize our knowledge of wetland responses in general. Now, I'm leading up the vegetation component with the assistance of Brian and Scott Zengel at RPI. And this presentation will try to summarize some of our findings. Now, I don't have time to go into detail as much as I might like to, but I will try to cover some of the main points and to provide a few representative examples from the literature to illustrate these points. Today, you will hear 4 presentations that address Deepwater Horizon impacts to coastal marsh vegetation and habitat, to nekton, and to community-related ecosystem services and human health. My presentation today on vegetation response will provide, first, a brief overview of the spill, then I'll describe the geographic extent and oiling severity, and I'll mention the wetland habitats that were affected, and then I'll get into addressing salt marsh vegetation, and I'll specifically talk about growth impacts. There are also in the literature impacts to genomics and physiology, which we'll have to wait for another time. Then I'll get into recovery and the importance of revegetation in that recovery and impacts to other wetland types if I have enough time. And then finally, I'll try to draw some conclusions and wrap up. So as we all are aware, it was on April 20th, 2010, that the Deepwater Horizon drilling platform exploded, resulting in the largest marine oil spill in U.S. history, and unfortunately costing the lives of 11 individuals. For 87 days, oil was released from the Macondo well into the northern Gulf of Mexico. About 4.9 million barrels of oil were spilled into the Gulf. Now, about 800,000 barrels were collected, leaving an estimated 4.1 million barrels moving towards the north central coast of the Gulf of Mexico. The oil was transported by currents and waves, weathered to different degrees, and finally reached beaches and coastal wetlands, as seen in this synthetic aperture radar image of Barataria Bay, Louisiana, by Garcia Pineda et al. Emergent coastal wetlands, including salt marshes, mangroves, and reed beds, as well as kilometers of beaches were oiled. And some of this oiling was extremely heavy. This is a SCAT, or Shoreline Cleanup Assessment Technique map from Michelle et al. And I'm sure most of you, if not all, have seen this before. And it shows the oiled and unoiled shorelines in the northern Gulf. And by far the largest volume of wetland oiling occurred in Louisiana. That's in contrast to Mississippi, Alabama, and Florida, which receive much less oiling to their wetlands. Michelle et al., based on SCAT data, reported that there were almost 800 kilometers of oiled wetlands, or 16% of the surveyed shorelines that were oiled. And then 2 years later, Nixon et al. published data based on SCAT and also other assessments of oiled shorelines, and estimated a larger amount of oiled wetland shorelines at about 1,100 kilometers. So that's about 17% of the wetland shorelines that they surveyed. So for argument's sake, let's just say that there was about 1,000 kilometers of wetland shorelines that were oiled, and this is for Louisiana, but also Mississippi, Alabama, and Florida. But remember, they had very few oiled wetlands. So this turns out to be about 600 miles of oiled shoreline, which is the distance from Houston to Baton Rouge and back. So this is not a trivial amount of oiling by any means. A number of different wetland types were exposed to the oil. So for example, if onto the Sasser et al. Vegetation map of 2013 for the Delta Plain of Louisiana, I superimpose oiled shorelines, which are these white lines that you see. You'll notice that salt marshes, the red polygons, were most affected. These salt marshes, like those around Bay Jimmy and the north central Barataria Bay, are dominated by two species primarily, Spartina alterniflora and Juncus romerianus. In addition, mangroves dominated by Avicennia germinans, which are embedded within the salt marsh polygons, were also oiled. And Avicennia exists not only in the area you see on this image, but throughout southwestern, throughout the coast of Louisiana and elsewhere. And finally, at the mouth of the Mississippi River, fresh and low salinity marshes of the Birdspit Delta, dominated by the common reed Phragmites or rosocane, were also oiled. Aerial images and photographs clearly show that marsh shorelines receive the brunt of the heavy oiling, with oil often extending from 5 to 10 meters into the marsh interior. As reference, the oiled shoreline indicated by the red arrow that I just put up is 10 meters in depth from the shoreline interface inland. But oil movement further than 10 meters was definitely documented. So oil incursions of 10 to 20 meters into the marsh interior, determined from either Macondo fingerprinted oil chemistry or from remote sensing, were documented. There were other measurements of oiling as far as 40 and 100 meters into the marsh. So based on the published literature, we can say that Macondo oil moved anywhere from 10 to 100 meters shore perpendicular into these marshes. However, we cannot rule out oil movement more than 100 meters, as oil might have moved up tidal creeks or remobilized by storms, as during Tropical Storm Lee in September of 2011, as documented in this photograph by Zangel et al. But we do have definite documentation of oil moving as far as 100 meters, at least in some marshes, and possibly further. Oil impact of vegetation can also be a function of whether the oil penetrated the soil, and this especially along heavily oiled shorelines, as you see in this photograph. Oil often pooled below the marsh vegetation and allowed oil to penetrate the soil in some locations, as you see here, especially during warm temperatures, times of warm temperatures. Although the highest oil concentrations were in the top 2 centimeters of the soil surface, as shown by research by Atlas et al., the Macondo oil also penetrated as far as 8 centimeters into the soil. And there are other data suggesting that oil in certain locations, these heavily oiled sites, may have gone even further. But this is an area that needed a lot more research to quantify. So not surprisingly, oil impacts also, certainly oil impacts depended on oiling intensity. This is no surprise. Oil impacts on plant growth were greatest with heavy oiling and less with moderate oiling, as shown by Linden and Mendelssohn for field results in Bay Jimmy. Hester et al. Found similar results over a much larger geographic area for the totality of the Louisiana Delta Plain. With more severe oiling, as indicated on the x-axis here, reducing vegetative cover. And similar effects were observed in the 2 years following the spill as well. Oil impacts were also dependent on distance to the shore-water interface, with impacts decreasing with increasing distance inland, as seen in this field study by Silliman et al. That occurred in Bay Jimmy. The negative effect of oiling decrease with distance inland was also shown in this remote sensing work by Canna et al. And they found that the negative effect of oiling basically ceased at 20 meters into the marsh. So the shoreline area and inland into 20 meters, there was a definite effect on the vegetation, but beyond 20 meters in their research, they found no effect of the oil. Interestingly, oil impact varied with plant species as well. Juncus romarianus was more sensitive to moderate Macondo oiling from Spartina alterniflora, as reported by Linden and Mendelssohn for the Bay Jimmy area. And you'll notice, however, that with heavy oiling, both species, both Spartina and Juncus, were completely killed. Willis and Hester found similar results for the coastal marshes of Mississippi and Alabama. So I'm not leaving out Mississippi and Alabama in this particular slide. Notice that Juncus, which is the stipple bars, decreased with increasing oiling level, while Spartina basically stayed the same. And this was true in the following year, the fall of 2012, where the stippled bars representing Juncus decreased with increasing oiling. So there's very good evidence that Juncus is much more susceptible to oiling than is Spartina alterniflora. It has long been recognized that salt marsh vegetation is resilient to oil spills. For example, in April 1985, a pipeline rupture released about 300 barrels of South Louisiana crude oil into this marsh just north of Empire, Louisiana, on the west side of the Mississippi River. Shortly after the spill, almost all the vegetation was dead as a result of both plant and soil oiling. But 1 year later, only minor recovery occurred, as you see here. In contrast, 3 years later, or 4 years after the spill, there was near complete recovery of the Spartina vegetation in this marsh, except for where mechanical damage during pipeline repair degraded the marsh substrate and where there were pre-existing ponds in the marsh. So findings like this, and there are many examples like this in the literature, have promoted the idea of salt marsh resilience to oil. Signs of recovery were also apparent after the Deepwater Horizon spill. Even at heavily oiled sites, some new vegetative sprats of Spartina occurred, as you see in this slide, in this photograph. Also, Phragmites produced new vegetative shoots from stems of oiled plants. And this, as you'll see in a moment, was extremely prolific. Silliman et al. Documented vegetation recovery from the Deepwater Horizon after only 2 years. Notice the difference in the proportion of live plants between impacted and reference marshes became less over time, continued to become less, and by January 2012, there was no difference between the proportion of live material in impacted versus reference marshes. So here we have recovery in 2 years. The degree of recovery, just like initial impact, however, varied with oiling intensity and distance from the shoreline. So certainly not all shorelines recovered as fast as what I've just described. For example, this graph from Lin et al. From the Bay Jimmy area shows that moderately oiled vegetation, those are the yellow bars, recovered to reference levels, the green bars, after just 40 months, While in contrast, heavily oiled vegetation, those are the black bars, did not recover to reference levels even after 48 months. So obviously, the extent of oiling has a major effect on recovery, as well as impact, initial impact. Distance from the shoreline is also a factor that impacted recovery, as seen in this remote sensing study of Khan et al., who found that it was not until 14 meters and further into the marsh that all pixels that were oiled and denuded of photosynthetic vegetation in September of 2010 had recovered and were classified in 2011 as photosynthetic, i.e. live vegetation. So we see that not only impact, but recovery was influenced by distance from the shoreline, which of course is related to the intensity of oiling, reduced oil levels as you move inland. Recovery, like initial impact, varied with plant species. This image shows a heavily oiled heavily oiled shoreline marsh composed of both juncus and spartina. And then 15 months later, plant recovery was underway, but only spartina regrew and colonized these heavily oiled shorelines. Juncus did not come back, supporting the actual data that we have on this. Shoreline erosion likely impaired recovery at some locations. We know that heavy oiling can reduce live below-ground biomass, as shown by the black bars in this figure from Lin et al. For Bay Jimmy field sites. As a consequence, soil shear strength, which is the ability of the soil to resist erosive forces, is reduced in heavily oiled marshes. Those are the black bars, but not moderately oiled, the yellow bars. This resulted in significant more surface erosion at heavily oiled sites. And marsh surface erosion can, of course, contribute to shoreline retreat. This is supported by the fact that when heavily oiled and mechanically cleaned shoreline plots were replanted with spartina, as done by Brittany Bernick and Scott Zengel, what was found was that shoreline erosion was reduced by approximately 2 meters per year compared to unplanted plots. So planting as a remediation, as a way of preventing shoreline erosion after a spill, was something that we learned as a result of this research. Although oiling often caused necrosis of above ground leaves and stems of Phragmites, regrowth from oiled stems was apparent and very rapid. These are new shoots from oiled stems in the greenhouse. The production of these new shoots was absolutely incredible. And that's what this graph shows, that with greater percentage of surface oiling of the vegetation of the Phragmites, there was this huge increase in these side shoots. And it was that increase in these vegetative shoots that allowed for above ground biomass to remain constant, even with 100% oiling. It was only oil added to the soil that had a significant effect in reducing growth. Avicennia, adjacent to shorelines, were significantly impacted by oiling, as found by Willis and Hester. When exposed to oiling in mesocosm experiments, Avicennia showed a reduction in the number of leaves above ground. These were for seedlings, and this was work done by Hughes et al. And also below ground biomass was significantly reduced by oiling. So we know that certainly Avicennia can be affected by oil spills. So in conclusion, we can say that the impact and recovery were dependent on shoreline oiling intensity, distance from the shoreline, plant species, and oil penetration of the marsh soil, especially for Phragmites. Lightly oiled shorelines typically showed minor plant impacts and recovered quickly, while impacts along moderately oiled shorelines were more significant and resulted in slower recovery. The most severe impacts, not surprisingly, were found in heavily oiled marshes, with impacts decreasing with distance from the shoreline. For both moderately and heavily oiled salt marshes, Juncus romerianus typically was more impacted than Spartina alterniflora and recovered more slowly, if at all. Recovery of both species was likely prevented along rapidly eroding shorelines, whether those shorelines had increased erosion due to oil or not. Phragmites dominated marshes, in contrast, although exhibiting dead leaves in many locations, had vegetation cover not significantly different from reference marshes, indicating the potential for rapid recovery. And finally, although limited published information exists for other vegetation types, including Avicennia, Avicennia dominated marshes adjacent to shorelines within this 1.5 meters were negatively impacted by oiling. And there is certainly much evidence for that. So with that, I'll end, and I'll be happy to answer any questions that you have at the end of the webinar. Thank you.
Thank you so much, Irv. That was excellent.